we do this. Pluses and minuses. This is where people get in trouble. Positive Q, negative Q. Well, that's pretty straightforward. I add heat, delta U goes up. Temperature goes up. Negative Q, heat is removed. Delta U decreases. Negative work. Negative W, work done by the system. Negative work, change in internal energy goes down. Temperature goes down. Plus positive work. Work is done on the system. Delta U goes up. Temperature goes up. On that. So, how do we apply these? Well, we have thermodynamic processes. Now, the only one that was talked about in the book was the adiabatic process. There are lots of thermodynamic processes. We put these thermodynamic processes together to describe thermodynamic cycles. Thermodynamic cycles is how heat engines work. Steam cycle for steam engines, an OTTO cycle for gasoline engines, diesel cycle for diesel, Brayton cycles for gas turbine engines, things like this. So there's these processes. Reverse Carnot cycles, how refrigerators work. Refrigerators are heat engines. And the first one is adiabatic. And now this is important to atmospheric processes. It's part of how your car engine works and things like that. But in this case, no heat is added for loss. In other words, Q is 0. Q is 0. No heat gained or lost. So that delta U, it's more like a V. Delta U is equal to the work done by or on the system. Done by or on the system. Well, I know what stupid trainers. Teen Talk trainer used this to do the drive race. What? They use this for the board.
Oh.
Well, they don't know. It looks about the same. I mean, basically, have to hide it. Never any more time. Now, how does this work? Well, one process is, these are important atmospheric processes. This is actually why there's a desert between the Rockies and the Sierra Nevada. Basin and range area between the Cascades and the Rockies is because of adiabatic heating and cooling. Forms what's called a rain shadow desert. Now this picture we're going to talk about, so we have Sacramento, Reno, and the Sierra Nevada mountains. Sierra Nevada mountains. And so what happens is you have this warm, moist air, and it is shoved upward by the Sierra Nevada mountains. Not because it's more or less dense, but the mountains physically, as the air moves up, they're moving up the mountain. Now this is higher pressure, warm air, and since it's higher, this starts to expand, the dew point goes, remember that relative humidity goes up, and finally we reach the dew point. That water starts to condense out, it forms clouds, rain, so some of the moisture comes out of it. It cools down, so it's cooling, and it comes up here, so we have this cold, moist air, but it's cold. Cold air rises or sinks. It sinks down, but there's less pressure. As it sinks down, that higher pressure air is going to compress it, and when it compresses it, it's doing work on it, the air starts to warm up, and the relative humidity is going to go down. This moisture, the relative humidity, because we get these low, warm, relatively dry, relative humidity is very low, so when it gets to Reno, is it ever going to give up this moisture? No. In fact, any moisture it encounters, is it going to come up in the air by evaporation? Yeah, these low humidities, and this is what causes that. The Chinook wind is adiabatic heating and cooling. The same thing happens in Denver. As the air goes out the Rockies, it rains on Denver and that side of the Rockies, when it goes over, Salt Lake City is really dry. It causes that area in between to be more deserty like that. Let's take a look at our thing here. So notice we're getting close, 94 degrees. Notice the air above it's increasing on that. Now we're starting to see some bubbles. Is this boiling yet? No. We're not 100 degrees. Notice where are the bubbles coming from? They're coming from the bottom. Why are they coming from the very bottom and not from the inside? Well, what can I say about the temperature of the bottom of the glass is touching the hot plate? Hot. Much higher than 100 degrees? Yeah, that's why it's up there. It's much higher than 100 degrees because of that. So we're not quite there, but we're getting close. Now the water is almost to the boiling point. Almost. Our air temperature is about 80 degrees, so we'll go on that. So, we come here. Another thing about adiabatic cooling, basically, as this air is being forced upward, every kilometer we force it upward, the temperature is going to go up beyond about 10 degrees. So if you're at sea level, basically the valley floor, you're at 25 degrees. Well, we have about a kilometer, which is about 3,000 feet. It'll have gone down 10 degrees. We go up another 10. So as it's going up, it is cooling off and things like that. Alright, so let's get back up here. Oh, it looks like 100. But notice they're both about the same, aren't they? They're not both the same. And what's starting to come out the top? Well, yeah, the steam's coming out, but notice up here, is this white stuff steam? No, that's actually water vapor, and I can put my hand there. I would not want to put my hand. There's a little hole on this side in the stopper, and it comes out, it's coming out ahead of that, on that. But notice what's happening in both of them. They're leveling out, aren't they? Which is what we've been saying, that as long as I have liquid water and gaseous water, and this is all gaseous water up here now, present together, they're not going to go up more. Now notice, temperature is about 101. Any reason why it's not at 100? Well, what can I say about the pressure on the water in this flask? Is it at atmospheric pressure anymore? Do you think it's higher or lower than atmospheric? Probably a little higher, right? That's what the gas bubble does. Makes it a little higher. And if going to the mountains where the pressure goes low makes the boiling temperature go down, if I raise the pressure, the boiling temperature is going to go up. That's the idea of a pressure cooker. In fact, this is how a nuclear reactor works. Nuclear reactors are what are called pressurized water reactors. Basically, when the reactor starts up, it starts to boil some of the water and it gets a steam bubble on top, and that pressurizes the water. So after a little bit of pressurizing, no more water boils, because basically you have liquid water going through the reactor. That's why when a reactor blows up, what they actually have is a steam explosion. The vessel gives way and it's steam that comes out. Fortunately, the steam is radioactive, but that's why they have another room around it to contain it. But reactors don't go like a big mushroom cloud. They don't do that. But notice it's staying level. Staying level. So write down a conclusion about that. Now we're going to see what happens when it cools off. So write a conclusion about that. So let's look up here. I'm going to take it off its heat source. Notice how quickly it stopped boiling. Did that take very long to stop boiling? Has the temperature of the water changed much? No. But now there isn't that extra energy to do phase change. Now it's going to take a while for water to cool down because it just takes a long time for water to cool down, right? It has to lose a lot of energy to that. But notice, since there was none of that extra energy coming in, boiling stopped. We stopped phase change. And notice, because there's none of that air, look what's happening to my air temperature. Very rapidly it goes down because there isn't that extra high energy molecules. Now, there's still high energy molecules going up there? Yeah. As many? No. But even now, notice my water is starting to go down in temperature. That really didn't take very long, did it? Doesn't really take that long. Okay, we'll come back and take a look at that in a little bit. Where am I? Oh, there I am. Okay. Alright, so, four-stroke engine. For ignition, I know there's 5 things. You say, well, there's 5 pictures there. How can you call a four-stroke engine? Ignition is not one of those. You can make an argument that ignition is part of compression or ignition is part of the power stroke. Basically what ignition does, and if we look at the Otto cycle, the graph of it, it actually belongs over here because when I ignite the gasoline,